So I've shown you the definitions of big O, big omega, and big theta, and they're the formal mathematical definitions, which are important to know. Like, you should know what those are. They should always be in your mind. But they're not always useful for showing big O, that a function is big O of some other function. Right, so let me give you a couple techniques, just a couple basic properties of big O that will help you when you're trying to establish the order of growth for a particular function. All right, so I'm going to call these properties, I'll write them down as theorems, right? So our theorem 1 is the addition theorem. Okay, so suppose I have two functions. I'll call them t1 and t2. So t1 is big O of g1 of n. And t2 is big O of g2 of n. Then I want to understand what the sum of these two functions is. So the question is, what is order of growth for t1 plus t2? t1 plus t2. Okay, and I'll just remind everybody that when I say t1 plus t2, I mean the function that is defined as t1 of n plus t2 of n, right? So what is this? Well, it turns out that the theorem here, the theorem statement is that t1 plus t2 equals big O of the maximum of g1 and g2. Maximum of g1, g2. All right, so let's think really quickly why this is the case, right? So what does maximum mean? Scroll this just a bit. I can even pinch it a little bit. What does the maximum of two functions mean? Well, let me just plot one. So suppose I've got g1 like this, g2 like this. So here's g2, here's g1. Maximum is defined as the following. It's defined as the pointwise maximum. So I'm drawing the maximum now in red. Right, so maximum is just everything on top when I plot the two together. So red here is max of the two, g1, g2. Right, so it makes sense that because big O is this upper bound property, it's this concept of less than or equal to, that the sum of two functions would be big O of the maximum of those two particular functions' orders of growth. So let's just prove this. Let's write out the full proof in generality so that we have this. So here I'm going to write the proof. So I have my assumptions already. So t1 of n is big O of g1 of n. What does that mean? That there exists a c1, and I'll say an n1, comma, an n1, such that t1 of n is less than or equal to c1 g1 of n for all n greater than or equal to n1. Okay, so that's the definition. That's the book definition of t1 being big O of g1. Okay, and the same thing for t2, right? So ditto, t2 of n is less than or equal to c2 g2 of n for all n greater than or equal to n1. Okay, scroll those above my head. Perfect. Okay, so what do we need? So we need to determine a c and an n such that something like this holds for the functions we're trying to show this for. Okay, so let's do this. So let's let c3 equal the larger of these two. So c3 equals the max of c1 and c2. So c3 is the larger of those. And then what is n going to equal? Well, so n, capital N3, is going to equal the max of n1 and n2. And n2, right? So we're just picking the bigger ones of all of these, right? So we're being conservative. We're making sure we don't miss anything. So then what do I have? Well, I have t1 of n plus t2 of n is less than or equal to what? Well, I know, so here's what I'll do. I'll say period there, and I'll say let little n be bigger than n3. So let n be bigger than n3. Okay, so now if n is bigger than n3, then it's also bigger than n1, and it's also bigger than n2. And so now I just get to adopt these two statements, right? I get to take those and drop them directly in. So what do I have? Well, I have that t1 of n is less than or equal to c1 g1 of n, okay? And I have t2 is less than or equal to c2 g2 of n. So that's good. So both c1 and c2 are less than or equal to c3. Okay, so this is less than or equal to c3 g1 of n plus c3 g2 of n. Okay, and I can just pull out the c3 and just take that out. That's easy. So this is equal to c3 times g1 of n plus g2 of n. Okay, and so now what do I have? Well, I've got this is less than or equal to the following. So this is a tricky little thing to try, but this is a fact, and I'll show you why. So this is less than or equal to c3. I'll just carry that through times 2 times the maximum of g1 of n and g2 of n. So 2 times max of g1 of n and g2 of n. Okay. So now what do I have? Just to round it all out, I have this is just equal to a c4. What's c4? It's just 2 times c3. c4 max g1 of n, g2 of n. Right, and so if I just combine these, a little bit awkward there. If I just combine these, what do I have? I've got that t1 plus t2 is less than or equal to some constant times the maximum of g1 and g2. Okay. Therefore, this piece is big O of this piece. Okay. So the takeaway is simple. The takeaway says plus is a lot like max. Okay. In big O, plus equals max, right? So if I ever say that a function's order of growth is something plus another thing, what I really mean is it's the bigger of the two. Okay, now I promised you that I would tell you why this inequality holds, right? Why can we go from here to here? Well, think if I have two numbers and they're both larger than 1, and then I take the bigger of them, and then I double it, that has to be less than the sum of the two originals. Or I mean, sorry, it has to be greater than the sum of the two originals. Okay, and so you can think of this just with numbers if you like, and then extend it in your brain to functions. But if I have 1 plus 2, this has to be less than or equal to twice the largest of them, right? This has to be less than or equal to 2 times max of 1 and 2, right? Which of course equals 4. Right? So this is the numbers answer to why that inequality holds.